Hi everyone, and welcome to my video on rates of change. My name is Darren from Maths Guru. Lovely to have you watching this video. Hopefully you're going to enjoy it. Now behind me are our learning objectives. Understand what it means to be an average rate of change and instantaneous rate of change. Be able to find average and instantaneous rates of change and be able to apply the learning to a number of different questions. Sounds easy. Now this is sort of building on a lot of the work we have been doing sort of previously and relating to differentiation. If you're not sure what and how to differentiate, there's videos on this previously on mathsguru.com. Totally free to sign up. But one of the most important things you need to know is about y2 minus y1 over x2 minus x1. Hold on, that's just the gradient. Yes, it absolutely is the gradient once again. And we know that for differentiation, we can find the gradient at one specific point on a function. Yes, because basically that's the tangent line. We can find the gradient of the tangent line. These questions come up ever such a lot. So what is a rate of change? I'm going to use a nice simple example here. A rate of change is basically you find 2 points on your function and you join them together and you find the gradient between those 2 points. So for example, if that was one of my points there and that was one of my points there, I can simply join them together with a straight line and then find the gradient by doing rise over run, or y2 minus y1 on x2 minus x1, right? So that there is an average rate of change, right? You choose 2 points on the function, use those coordinates, whatever. Again, if I want to find the instantaneous rate of change at that one specific instant, because what you can realize is as we work around this, every single instant has a completely different gradient, right? So every single point has a different gradient. So if I wanted to find the gradient of that point there, then I would use the differentiation that we've done before. Examples. For a function with the rule f of x equals x squared plus 2x, find the average rate of change for x in 2, 3. So basically what they're saying is whatever that graph looks like, I'm looking for the 2 coordinates where x equals 2 and x equals 3. I'm going to find the values of y for each of those. Well, how am I going to do that? Substitute in. Yep, so that's going to be there for f of x, which is going to be, in this situation, my value of y1 is going to be 2 squared is 4, plus 2 times 2, which is 4, which is going to give me 8. Here, my f of x, which in this situation is going to be y2, because that's going to be my x1 and my x2, is going to give me, well, I've got 3 there. 3 squared is 9, plus 6 is 15. And so therefore, my average rate of change is going to be y2, 15, minus 8 over 3 minus 2, which is going to give me 8, 9, 10, 7. Right, so my gradient there, as far as I'm concerned, is going to be 7. The question moves on, find the average rate of change for the interval 2 plus h. Okay, so we get a little bit more tricky now. Doesn't this remind you of differentiation from first principles? Oh, yes, because it's the same idea. Right, we already know that for x equals 2, we have y is equal to 8. So we can reuse that. Now we're going to do 2 plus h. So when x is equal to 2 plus h, what is my y going to be? Well, it's going to be 2 plus h all squared plus 2 lots of 2 plus h, which is going to give me 4 plus 4h plus h squared plus 4 plus 2h, which is going to give me 4 plus 4, which is going to be 8, plus 4h and 2h gives me 6h plus h squared. Right, so my average rate of change there is going to be given. So therefore, average rate of change, let's call it arc for a moment, is going to be given to y2, which is h squared, plus 6h plus h, 8, minus 8, which is y1, divided by 2 plus h minus 2. It is differentiation for first principles, because that 8 and that minus h cancel, that 2 and that minus 2 cancels, which gives me h squared plus 6h divided by h, and we now know that h can cancel into all of those to give me simply h plus 6. I think h plus 6. Yep, or 6 plus h, either way. The instantaneous rate of change of f with respect to x when x is equal to 2. Well, basically, if we differentiate our function, so let's hopefully have got enough room here. So f dashed of x gives me 2x plus 2, and therefore, when I substitute, what did they want in? 2, I think it was. When they substitute 2 into there, it's going to be 4 plus 1, which gives me 6. Ka-ching! Thank you very much. Now, again, this is a CAS course. We could have used the CAS to be able to help us. A balloon develops a microscopic leak and gradually decreases in volume. Its volume V cubic centimeters at a time t seconds is given by that. Find the rate of change of volume after that. It's not asking for average rate of change. It wants rate of change. So it's instantaneous rate of change after 10 seconds. So for A part 1, let's differentiate it. So we're going to get the dV by dt, all right, which is going to be my rate of change, is going to be given by 600 goes, minus 10t is just going to give you minus 10, and then that's going to give me minus 2 on 100 times t. All right, so that's my differential. Now, when I substitute 10 into that, what am I going to end up with? So dV by dt is going to give me minus 10 times minus 2 times 10 on 100. That's going to cancel. So you get minus 10 minus 2 on 10, which is going to basically give you minus 10 and 1/5. Right? Again, it's just sort of shortcutting that because you can sort of do that. All right. So my rate of change there is going to be centimeters cubed per second. All right, because they give me the volume. They give me the volume in centimeters cubed and seconds. 20 seconds. Well, again, if I wanted to do a part 2, then in which case my dV by dt, you would just substitute 20 into here. And what's going to come out is, shortcutting this, is going to be basically 10 and 2/5, or minus 10 and 2/5 centimeters cubed per second. All right, so my change in that minus sign basically means it's decreasing. That sort of makes sense, doesn't it? Because my balloon is basically got a leak. And so my volume should be decreasing as the air is escaping. It should have a negative value. Now, it says how long could the model be valid? Now, again, in this situation, believe it or not, I would fire up Desmos. Why would I fire up Desmos? Well, it makes life a lot easier if I can see what this looks like. 600 minus 10t minus 1 on, on 100. So used to using the CAS calculator, t squared. All right. Now, the problem with this is I've done t. Desmos doesn't understand what I'm talking about. So let's change that to x. And we, fingers crossed, if I just do y equals now. Where's my graph? Well, if I zoom out, we're probably going to find out that there is my model there. Now, hold on a moment. Something doesn't seem quite right here. Why? Because if we look at that particular thing, first things first, it says t has to be greater than or equal to 0. And if you're not sure why, it says here t has to be greater than 0. Hopefully, you also realize that time can't be negative. So I can do that here by saying t is greater than 0. So put some inequalities here. I've done it again. Oh, it's been a long day. X is greater than 0. Oh, cool. There we go. So now my graph makes a lot more sense. Yes or no? Why? Because again, we have to think practically about what does this section here mean? Well, bearing in mind my axes are volume against time, it's also not possible to have a negative volume. So in which case, we would be looking for that intersection there to say for how long could the model be valid. It could only be valid for 56.72644 seconds, all right? So the problem with Desmos is that doesn't do that in a nice exact value. So now that I know what I'm sort of looking towards, how can I find it? What I'm looking to solve for where this is equal to 0. All right, so bringing back my screen, I'm now looking to say, well, so let's do part B here. We're trying to solve for 0 is equal to 600 minus 10t minus 1 on 100t squared. Now, because this is a modeling question, it is highly likely it's going to be on a CAS calculator. So if I ring my CAS up, what I'm now going to do is solve. 0 equals 600 minus, what I've got, 10 times t. I always put the times in, by the way, minus 1 on 100 times t squared, comma t, and I'm going to put pipe t is greater than or equal to 0. There we go. And out comes my answer of so t is equal to, let's turn my calculator off for a moment, 100 root 31 minus 5. Now, is that my answer? Well, not really, because you've got to basically turn around and say, well, there's a range of values here because t has to be no smaller than 0. So t is going to become between that 100 and root 31 minus 5. Okay, and that, I think, would be our correct answer. A pot of liquid is put on the stove. When the temperature of the liquid reaches 80 degrees centigrade, the pot is taken off the stove and placed on the kitchen bench. The temperature in the kitchen is 20 degrees. The temperature of the liquid, T degrees C, at any time T is given by that. Now, again, this is about cooling, and hopefully you realize a little bit of physics, a little bit of thermodynamics, that while the liquid is undoubtedly going to start at 80 degrees C, it's only ever going to plateau out at 20, because as soon as the temperature of the liquid reaches the external temperature, it's going to be the same. So we are looking at it to probably do something like this. All right. And again, if we were to plot that, but undoubtedly we will in a moment, we'll have a look. So the temperature of the liquid at time t minutes is given by, right, cool. So let's look at part A. And notice with all these application style questions, I try and think about what it might look like in real life. Find the rate of change of temperature with respect to time in terms of t. What they're really asking you then is dt by dt is equal to, well, 20 goes. When we differentiate logs, or natural logs, we're going to do minus 0.3 times 60. So we're going to do 60 times minus 0.3 times by e to the minus 0.3t, which is going to give me minus 18e to the minus 0.3t. Ka-ching. Relatively simple question. Now, moving on to part B. Oh, this was tricky. All right, B part 1. What we notice is we've been given our values in terms of capital T, not little t. Because here's a problem. My dt by dt here is actually in terms of my little time. So is there a way I can actually get this in terms of capital T? Well, if I know that capital T is given by 20 plus 60 e to the minus 0.3t, we know that we've got e to the 0.3t here. So I'm now going to take 20 from both sides, divide by 60, and there we go. So now when I see e to the minus 0.3t, I can substitute that. So that's now actually the same as minus 18 times t minus 20 on 60. So now I've got it in terms of t. Life is good. We can do this. So now when t equals 80, I know that dt by dt is going to be given by minus 18 times t, which is 80, minus 20, divided by 60, which is going to be 80 minus 20, 60. 60 divided by 60 is 1. And so it's going to be minus 18 degrees C per, oops, not T, per second. So this then is going to, is basically going to cool at 18 degrees per, did I say second or minute? Let's try that one again. Minute. What about part 2? Well, dt by dt in this situation is going to be what? T equals 30 minus 18. 30 minus 20 over 60, which is going to be minus 18 times 30 minus 20 is 10 times by 1/6, which is going to be minus 3 degrees C per minute. And notice how quick and easy it was for a question to try and trick us by actually giving us capital T and not little t. And the reason I worked that out was because I substituted it in as little t and I got really horrible numbers. But that's okay. It's a learning experience. VCAA past paper question. Right. So again, here's a past paper question from 2023. The following diagram, and just to try and make it easy in terms of space, represents an observation wheel with its center at point P. Passengers are seated in pods, which are carried around as the wheel turns. The wheel moves anti-clockwise. Thank you very much for the arrow, with constant speed, and completes one full revolution every 30 minutes. Now, this is built up into a much, much bigger question. When a pod is at the lowest point of the wheel, point A, it is 15 meters above the ground. The wheel has a radius of 60 meters. Consider that function there. So we've got h of t equals minus 60 cosine of bt plus c for some b and c, which are real numbers, which models the height above the ground of a pod originally situated at point A after time t. Now, there is a lot of words here, and VCAA, make no apologies for this, because it's about understanding which parts of this is going to be useful at any one time. C, find the average rate of change in meters per minute of the height of a pod on the wheel as it travels from point A to point B. Now, what becomes important here is actually in part A, you had to show that question to find the values of B and C. It's very common to have a show that question, because if you couldn't find the values of B and C here, then actually you'd be in a world of hurt, simply because, well, you wouldn't be able to finish the question. So what we now know is that h of t is given by minus 60 times the cosine of b, which was pi on 15 times t, plus some value of c, which was 75. So if we now look at the height when time is 0, what do we know? Well, we didn't need to work that out, to be perfectly honest with you, because we know that A has a height of 15 meters. So we know at time equals 0, h of 0 is equal to 15. Right. It takes how long? 30 minutes to do a full rotation. That came from this question here, which means to do a quarter of a rotation, it's going to do 7.5 minutes. So t at 7.5, and we want h of 7.5. Now, again, I can't do that in my head, so it would mean that I'm probably going to have to fire up my calculator. And what we got here then? So we got minus 60 times, he said, oh, I've done it again. I don't know why that keeps doing that. It's annoying. Minus 60 times the cosine of pi on 15 times 7.5 plus 75. Right, there we go. It's going to be 75. Oh. I'm fairly sure people are now shouting at me as if to say, well, hold on, you could have worked that out, because we already know that the radius is 60, so that's 30, and that's radius of 60. Try that one again. So we know that's 60, and we know that would be 60, and therefore that's 15, and so that would have to be 75. Okay, I did a lot of work there, but that's fine. I'm glad it came out with the right thing. Again, being a 1-mark question, it's not really expecting you to do a lot of hard work. So my rate of change, therefore, my average rate of change is equal to y2 minus y1 over x2 minus x1, which is time 2, 7.5 minus 0. So 75 minus 15 gives me 60. I'm going to divide that by 7.5, hit enter, and I get 8. So therefore, it is going to be 8, what was it, meters per minute. There we go. So that's my average rate of change. End of the video. Thanks for watching. If you can, subscribe to my YouTube channel. That would be massive. Have we understood what it means to be an average rate of change and instantaneous rate of change? We have. Have we been able to find average and instantaneous rates of change? We have. Have we applied that to a range of questions, including some VCAA questions? We have indeed. I'm done. Thank you very much for watching. Hopefully you found it useful. If you have, leave a comment on my YouTube channel if you're watching it through there. Otherwise, I'm going to continue recording some videos, and hopefully you're finding them helpful. Well, until the next time I see you, please take care. And if I don't see you again, stay safe. Bye-bye.